This session is going to be about assignment 1.5, comparing the properties of liquids and gases and solids. And really it's mostly going to focus on liquids because there's a lot to talk about there. So it starts out with this idea of having a certain amount of water and you measure out a certain volume of the water like this and can figure out things about the force and the pressure going on inside of it. So they start out with explaining that the weight of water filling this space is equal to the amount of force pushing down on the bottom surface in that area. And that makes sense because weight, what we call weight, is just the force of gravity acting on something. So if you measure out this much water and figure out how much that water weighs, that's how much force is pushing down here on the bottom. So the weight of this water and therefore the force pushing on the bottom surface can be calculated. And it shows us two ways to do that. So first, if we know the mass of the water, so again, this amount of water is measured out. If we are given the mass, then it's pretty simple. We just use our formula. Force is mass times g. So force in this case is the force of gravity, which is a weight. So we're finding the weight. Mass would be given in the problem, and lowercase g, as we've learned before, is always, always, always 9.8 meters per second squared. So as long as you're on Earth, that is the number you put in for g anytime you see it in a problem. So if we know the mass, it's pretty simple. We just take mass times 9.8. That tells us the force of gravity pulling down on the water, which is the weight of the water, which is also the force with which the water presses on the bottom of the water. Now, the other way to do this is if it doesn't tell you the weight, the mass. So if you're trying to find the weight of the water, but you don't know the mass, there's this other formula you can use, which is force is area times height times density times gravity. So area is just this bottom surface area that's colored red here. The height was literally just measuring the height of the column of water. So from the bottom all the way up to the surface, you measure the height. Density is how much water is in a certain volume. We're going to talk about density on the next slide. And then G is always 9.8. So you just multiply those four numbers together, and that tells you the force of gravity or the force with which the water pushes down on the bottom. So let's talk about what that density is. Density is the amount of mass smushed into a certain area. It's measured in units of mass over volume. And so density of water is a really important number. It's 1,000 kilograms times meter cubed. You need to know that number. Write it down, memorize it. You're going to use it in other formulas. If you need to know any other liquids, it will tell you the densities of different liquids, but you need to know water, 1,000 kilograms per meter cubed. And again, that's going to go into formulas like the previous one anytime you see a D for density. Now, once we've talked about force, we can talk about pressure. Pressure is the amount of force in a certain area. If force is spread out, the pressure is lower than if it's concentrated. So you can think of this about just in everyday life. If you poke yourself on a pin or a needle, it's the pointy end that hurts because all the pressure, all the force, I'm sorry, is being concentrated into that small, sharp area. Where if you touch the back end of a nail, the head of the nail, that doesn't hurt because it's flat. So the force is being spread out over a larger area. So it's that same concept, but we're talking about it now in a liquid. And later we'll talk about it in a solid as well. When we're talking about pressure, the units that we use is called Pascal. It's named after a person, so it's capitalized as PA. And a Pascal is 1 Newton of force over 1 meter squared of area. When we're talking about pascals, sometimes in our problems we'll also be using kilopascal. So kilopascal is just 1,000 pascals, but it's abbreviated KPA. And here's the formula that you would need to get that. So if you do a problem and you get your answer in the units of pascals, and you find out, oh, it's actually asking for kilopascals, what do I do? You just take your pascals, you divide by 1,000, that tells you how many kilopascals you have. Now, another formula for finding pressure in a liquid column, we could also use pressure is height times density times G. So height is just going to be the height of the water column again from the bottom up to the surface. Density, remember the density of water is 1,000 kilograms per meter cubes, and that is wrong. That says 1. That should say 1,000. I'm so sorry about that. 1,000 kilogram per meter cube. Don't forget that number. And then G is always 9.8. So pressure in water is pretty easy. Height times density times G. The only way to change the pressure, and this is kind of important to know, is just by changing the amount of water, the height of the liquid column. So area doesn't have an effect. So we talked before about pressure, and we said pressure is force over area. When we're talking about liquids, there's some other things happening, and area actually doesn't matter. And if you want to read in your study guide, your reading assignment, it does explain why area doesn't matter. We're just going to skip over that for now, and I promise area won't matter. So the only thing that changes the pressure in a liquid is the height of the water column. So there's more pressure in this deeper water than there is in this shallow water. And it wouldn't really matter if we picked, a narrow area and measured it here in the deep water, it's still going to be the same. Okay, the only way to change the pressure in liquid is to change the height of the column of liquid. One more thing about this formula is you could use the same formula for finding the pressure on an object within the liquid column. The only difference is where you measure height. So I'm going to go back. We measured height before, saying, okay, the depth of the water entirely, that's our height. But when we're talking about an object in the water and you want to find out how much pressure is pushing down on it, on the top of it, then height is from that point up to the surface. Okay, so that's the only difference about just measuring the water or measuring an object in the water. So Pascal's principle has to do with pressure, and it is important to know that liquids cannot be squished. You can't change the volume of a liquid. So with a gas, with air, you put more pressure on it, you'll squish it together and it'll take up less space, but that doesn't happen with a liquid. When force is applied to a liquid, it stays the same volume, and the pressure within the liquid just increases. And this is a part of Pascal's principle. Adding pressure at any point will send an equal amount of pressure throughout the whole thing. So here we have some liquid on the bottom, the blue part, and we have a piston on the top of it, and it's pressing down with 100 kilopascals of pressure. And what's that going to do is make the liquid have 100 kilopascals in pressure pushing out in every direction. So that's important for Pascal's principle. The pressure stays the same throughout the entire liquid in all directions. To find the amount of pressure being applied, so we know the pressure is equal all around, but let's figure out how much it is. Now we're back to this formula of using force over area. So example would be with this piston, you can just measure the area of the piston and the force, and that'll tell you the pressure. However, sometimes we have formulas where they don't tell you the force. So we're back to this problem of we need force to find pressure, but it doesn't tell us force. So that just becomes a two-step problem. Instead of force, it will give you the mass, and then you could use this formula. Nope. Force is mass times gravity. Sorry about that mistake again. So force is mass times gravity to find the force, and use that once you find the force to plug into that pressure formula and find pressure. So it will look something like this, where you have a liquid down here, you have a piston on the top, and it's got a mass of 6 kilograms, but it doesn't tell you the force, just here's our mass, it's 6 kilograms. So you can take 6 kilograms times G, which is 9.8, it's always 9.8, and that tells us the amount of force pushing down. And then once we know force, Now we can again plug that force number, which in this case is 58.8. We took 6 times 9.8, got 58.8. So that's our force. Now we put that number back into this problem here, and we take our new force divided by area. So 58.8 divided by 0.588 gives us our area of 100 or our pressure of 100 pascals. So let's look at an example problem of this. This is a practice question from your study work. A piston above a liquid in a closed container has an area of 0.75 meters squared, and it carries a load of 200 kilograms. So this looks just like the previous slide where we have liquid on the bottom, there's a piston pushing down on the top. So what will be the external pressure? Well, pressure is force over area, but we don't know force. It doesn't tell us force. So step 1, find the force. Force is mass times gravity. So the formula is written correctly here. I'm sorry about the last slide, but we've got force is mass times gravity. So it tells us our mass. Our mass is 200, so that gets put in here. Gravity is always 9.8, and so our force is 1,960. And that would be in the unit of newtons. Now in step 2, is actually finding pressure. So pressure is force divided by area. So here's the force that we just found, 1,960 divided by the area that it gave us in the problem, so 0.75 goes here. And that gives us our final answer, 2,613.3 pascals. Now, a use of Pascal's principle is a hydraulic press. So remember, when you have the pressure of 100 pascals, throughout the whole thing, the pressure does not change. It stays at 100 pascals. So if we have a small piston pushing 100 pascals of pressure, and then that pushes on a larger area piston on the other side, it's going to still have the same amount of pressure, but because it's applying that pressure over an even larger area, it's going to actually make the force greater. So you could see this small piston here had a force of 58.8 newtons. It made a pressure of 100 pascals. Over here we have the same 100 pascals over a different area, and so it's making a bigger force of 300 newtons. So that's using Pascal's principle. It's called a hydraulic press, and that's the whole idea, is you have the same amount of pressure, different areas, that's going to result in different forces. And before we move on to the next thing, we need to go over one more formula for force. So we've looked at a few different ways to solve force, and here's one more. This works for both solids and liquids. The force of gravity is equal to the volume times the density times g, which is 9.8. So we're going to use that in this next idea. Archimedes' principle is that objects falling into water will push the water out of the way. They'll displace the water. And as they push the water out of the water pushes back on the object with a buoyant force. And that buoyant force is equal to the weight of the water that's displaced. Okay, so again, it's pushing that water out of the way. The force that puts back is equal to the weight of the water that got pushed out of the way. And why this matters is the buoyant force works to partially cancel out gravity. The apparent weight of the object is less. So the object, if it's out in the air, just sitting on a table or something or falling, it's going to have a certain weight. And that's kind of what we can think of as the real weight of the object. Then you put it in the water, the buoyant force is working against that weight. Okay, gravity is pulling down, but the water is pushing up. So it makes the weight of the object appear to be less. Okay, so we call that the apparent weight. You'll see questions in your work and in your test where it refers to the weight of the object in air and the weight of the object in water. So that's what the difference is. Oh, the weight in air is just the normal weight, and the apparent weight is the weight of the object in the water. So let's look at an actual practice problem using this formula. A concrete block has a volume of 0.10 meter cubed and a density of 2,000 kilograms per meter cubed. And what is the weight of the block in air and what is the weight of the block in water? So again, the weight of the block in air is just normal. How much does this block weigh? So we calculate that with the formula we just got, volume times density times gravity. So again, there's different formulas that you could use. Because we were given volume and density, this is the one we're using. So force is equal to the volume, which was 0.1, so that goes here. Density was 2,000, and G is always 9.8. And we multiply them and get our answer of 1,960. So that's how much the weight of the block is. Now the next step is what is the weight of the block in water? So to do that, we've got to figure out a couple things. We need to figure out what the buoyant force is, because remember, that's what's working against the weight, is the buoyant force. And we learned before, buoyant force is equal to the weight of the water that's displaced by the object. So to calculate the weight of the displaced water, we're using this formula. Okay, so force is volume times density times gravity. So the volume is going to be the same. The block is 0.10 meter cubed, so that means if it's submerged in water, it's pushing 0.10 meter cubes out of the way. Our density of water is always the same, 1,000 kilograms per meter cube, and gravity is always 9.8, so we multiply those and get 980. And we are still not done. All we did was find the weight of the displaced water. But that is equal to the buoyant force. So we know the weight of the object, we know the buoyant force of the object, and then we just subtract them to find the apparent weight while it's in water. So 1,960 minus 980 gives us 980. And that is the force of gravity acting on the concrete block in water. So that was a lot about liquids. We're going to go really fast over solids and gases. Gases are compressible. The pressure that you put on a gas will actually squish it down, make the molecules closer together, and that's called compressibility. And when pressure is removed, so that there's less pressure, the molecules can spread apart more, take up more space. That's called expansibility. Okay, and there's a quick diagram here showing it. With more pressure, they're closer together, they're squished down. The same number of molecules with less pressure over here are spread out. When we talk about atmospheric pressure, this is the pressure that the atmosphere just always has. The atmosphere is 1,000 meters thick, 1,000 kilometers thick. So there's a lot of air that's always just pushing down, weighing down on us. So that is pressure that's just always there. So when we measure the atmospheric pressure, they measure that with barometers. So there's an average that we call the standard atmospheric pressure, but it does change depending on where you are, and it changes with the weather. So we have barometers to measure pressure. So standard atmospheric pressure is just kind of always there, but then there's also times when we add additional pressure. So for example, when you fill your tires on your car with air, there's a certain amount of pressure they should have. Maybe your tires should have 32 psi, which means 32 pounds of pressure per square inch. So that's using the English system instead of the metric system, but that's just an example you might be familiar with, so that's what we'll stick with. So if you're looking at your tires, they've got 32 psi. That's in addition to the atmospheric pressure. So we're taking the atmospheric pressure and we're just kind of ignoring that. We're setting that as sort of a baseline of 0, and then we're saying on top of that, we need to add 32 pounds of pressure per square inch. So that is what we call gauge pressure. That's the extra pressure from a mechanical device that's on top of the atmospheric pressure. So we use that a lot in real everyday life. But sometimes in science, we need to know, well, what is the absolute total pressure? We're taking the atmosphere plus the gauge pressure on top of it, and we're considering all of that. That's called absolute pressure. So you take gauge pressure plus the atmospheric pressure, and that gives you the absolute pressure. So that's something that you'll use more in the next lesson, but just want to introduce it a little bit here. And when we talk about solids, they have some important properties, and some of them are conductivity or insulation. So conductivity is the ability to allow heat to be transferred. Solids are usually better conductors than liquids because the molecules are closer together, and liquids are not that great, but gases are even worse. Gases are poor conductors, but moving air, so if you have a gas where the air is moving, so the wind is blowing past you, it actually can transfer a lot of heat because it picks up a little bit at a time, but it moves it away from you. The opposite would be insulation. That's the ability to prevent heat from being transferred. And a really, really good insulator is air that's not moving. It's called stagnant air. So you can trap air somewhere so that it's not allowed to move away. It's actually a very good insulator. So solids that have a lot of air pockets that can hold stagnant air, such as down inside of a parka or a big jacket, it's very fluffy. It's holding all that air in there. Or the insulation in the walls of your house. There's a lot of air pockets in there and they're holding the air there. So those are acting as insulators. And in solids, we talked about pressure. And this kind of brings us back to the very beginning of this lesson when we were, well, not this lesson, this section, where we were talking about pressure being force and area. So pressure is force over area. Increasing the force would increase the pressure, but also decreasing the area will increase the pressure. So this is what I was saying earlier about how you could feel the pressure on sharp or pointy things a lot more easier than flat things. If you put your hand on a thumbtack that's pointy side up, it's going to hurt. But if you put your hand on a thumbtack that is the other way, the flat side up, it's not going to hurt as much because all of that force is spread over a bigger area instead of just being on that tiny point. And this is just a quick illustration of it, but you can see if these two objects have the same weight, they're going to apply different pressures. The one over here is putting all that weight onto this one tiny little point, and the one on the left is putting all that weight spread across a pretty wide base. So that's the difference in pressure, even though it's the same amount of force. And that is all that we have time for today. But if you have any more questions about this lesson or any other lessons in physical science, this is how you would be able to contact your instructor.